Hi all, we're taking a look at the Achieve assignment for section 10.2. There were some good problems here dealing with the series in this section. The first problem has 4 sub-problems, part A, B, C, and D here. Let me go ahead and break apart each one of those for you. So the first one's going to give you something like, or part A is going to give you something like 1/4 plus 1/16 plus 1/64 plus 1 256. And it's asking you to write that, please notice, as an nth partial sum. So some function for the nth term of that series. And so what we say is, well, and what I did is I just looked at it and said, well, clearly the denominator is just powers of 4. So it's 1/4 to the first, 1/4 to the second, 1/4 to the third. So the a sub nth term, you can just say, well, you're going to say plus dot, dot, dot. The nth term of this series is just always going to be 1/4 to the n. Thus, that's the answer that I inputted into Achieve for a very easy first problem. Now, part B of this first problem, my series was as follows: 1/1 plus 4/3 plus 16/9 plus 64/27. So here's the logic that I used in this problem. As I go from this term to this term, clearly I need to multiply the numerator by 3 and the denominator by, my numerator by 4 and my denominator by 3. So I'm multiplying by 4/3, and I can see that that multiplication of 4/3 is going to continue here and here. But that first term is not 4/3 to the first power. It's 4/3 to the 0 power. The second term is 4/3 to the first. The third term is 4/3 to the second. So I just said, well, how about I just say that this is 4/3, and then in order to make sure when n is 1 that I get a 1, I just said, well, let's raise this to the n minus 1 power. That way when n is 1, this 4/3 is to the 1 minus 1 to the 0 power. Any number to the 0 power is 1. And then it's going to account for the correct fraction for every term thereafter. So I can say, okay, 4/3 to the n minus 1 power handles that expression, no problem. The next one, I had 1/1 minus 2 squared over 2 times 1 plus 3 cubed over 3 times 2 times 1, and then minus 4 to the 4th over 4 times 3 times 2 times 1. Well, the denominator, easy. I just looked at that and said, well, that's clearly the factorial. A factorial is defined as n factorial is n times every integer value less than it all the way to 1. So clearly that's 4 factorial, that's 3 factorial, that's 2 factorial, that's 1 factorial. So my denominator is n factorial. My numerator, I can say, well, I have 1 to the understood first, 2 to the second, 3 to the third, 4 to the fourth. So I can say that numerator is just n to the nth power. And then out in front, I handled the alternating sign by just saying, I know that that's going to be -1 to a power. Now, I needed all of the odd terms of n to be positive terms and all the even terms of n to be negative. I can handle that by just saying -1 to the n plus 1 power. Could have also done -1 to the n minus 1 power, would have also worked. However you do it, you know that that first term needs to be positive. Well, -1 to the 1 plus 1 is -1 squared. It's going to ensure that your first term's positive, and it will ensure that every even term thereafter is negative, because 2 plus 1 would be 3, 4 plus 1 is 5, and -1 to any odd power is going to give you the negative out in front. So that accounts for that. I could see students really struggling with this next one. It's tricky, but fun nonetheless. The denominator is easy. You can just say, well, if this is the first term, second term, third term, fourth term, then this denominator is always n to the second power plus 1. So no problem down there. My numerator, I know it's always at least 1 and sometimes greater than 1. Let's see if I can make this a little more clear. Yeah, that's better. So it's at least 1. So I started off with a 1. Now, sometimes I won't add anything to that, and other times I'll add a 1 to that. How can I handle that? Well, here's one nice way. You could say, how about I do -1 to the n plus 1 power plus 1 over 2. Now, think about what that's going to do, guys. For the first term here, you'd be saying 1 plus, and it'd be -1 to the second, so that's going to be a 1. And then 1 plus 1 is 2. 2 divided by 2 is 1. It's going to give you a 1 plus 1 in your numerator. What about for any even term, like the second term and the fourth term? Well, anytime I have n as an even number, this power is going to be odd, which makes this just -1. And -1 plus 1 would be 0. You'd be adding a 0 to your 1, which is precisely what you want it to be. And that's going to make for every even term, the numerator is going to be 1, which is what we want. Now, for every odd term, we know that this exponent's going to be even, making this a positive 1, and you'll have your 1 plus 1 is 2, 2 over 2 is 1, 1 plus 1 gives you the 2. This is going to account for every single term throughout your entire series. It's a beautiful problem there. Tricky, but beautiful. And you'll see here that all of those answers, and actually I have to scroll down to get to the last one, all of those answers are like what I entered in to achieve. Up next, we're asked to create the nth partial sums for s sub 2, s sub 4, and s sub 6. So the partial sum is just the sum of the first n numbers of the series. If I want s sub 2, that's the sum of the first 2 numbers of the series. S sub 4, the sum of the first 4 numbers. So what I went in and did is I said, well, my sum of the first n numbers would be, and this is just your series given, 1 over 4 squared plus 1 over 8 squared plus 1 over 12 squared plus 1 over 16 squared, and so on. Now, for the second partial sum, I'm going to say, well, that's just the sum of the first 2 numbers. So that's going to be 1 over 4 squared plus 1 over 8 squared. It's 1/16 plus 1/64. I just went in and said, well, 1/16 I know is 4 over 64 plus 1 over 64 gives me 5 over 64. Now, what's your fourth partial sum? Well, your fourth partial sum is your second partial sum plus the third term and the fourth term. So you just say, well, it's the sum of the first 4 terms. I already know the sum of the first 2. So the only thing I'm adding is the third and the fourth term. Now I just used my calculator to simplify that expression to 205 over 2,304. And then you say, well, okay, now the sixth partial sum. Well, the sixth partial sum is the sum of the first 4, which we already have right here. And now you have to understand what the fifth and sixth term of this series would be. And you can see the denominator, it's always going up by a factor, or well, not a factor, but the pattern here, 4 squared, 8 squared, 12 squared, 16 squared. The next denominator would be 20 squared, and the next one after that would be 24 squared. So that's where these 2 terms came from. This is the fifth term of the series. This is the sixth term of the series. So the sum of the first 6 numbers, s sub 6, would be the sum of the first 4 plus the fifth plus the sixth term. And again, I just simplified that to fractional form and got 5,369 over 57,600. Pretty nice. Now, I think in that one, my calculator gave me some distress in converting it to a fraction. So I went in and multiplied the decimal answer I got by 576, which was 24 squared in this case. And so I had to kind of figure out the fraction on my own, but that's just arithmetic. I'll let you do that if your calculator causes you any stress. For the next question here, it's asking us to evaluate again the second, third, and fourth partial sum of the series -1 to the k times k to the -2, and this is from k equals -1 to infinity. Okay, so what I did here, if I said I'm trying to find the sum of this series, well, the sum of the first 2 terms, you just say, well, it's your first term plus your second term. Now this negative 1 to the k is going to make every odd term of the series negative. So that's why we have a negative first term and a positive second term. I'll have negative 1 over 1 plus 1 over k squared, which is going to be 1 over 2 squared. So I get negative 1 plus 1/4. That gives me s sub 2 is negative 3/4. Now s sub 3, that would be the sum of the first two terms plus the third term. Well, you know the third term of the series, it's going to be negative because of this, and then you'd have times 1 over 3 squared, well, minus 1 over 9 there. So you have negative 3/4 minus 1 over 9, got a common fraction to negative 31 over 36. S sub 4, now I went back to S sub 2 for some reason, but that's okay. I could have started there and then said plus that. But S sub 4 is also S sub 2 plus the third term, which is being subtracted, plus the fourth term, which is going to be 1 over 4 squared. And so you could have just said it's the negative 31 over 36 plus 1/16. And when you do that, you'll get your negative 115 over 144. Pretty straightforward there. For the next question, again, it's kept with that common theme of finding the nth partial sum. This one was wanting the S sub 2, S sub 4, and S sub 6. And it said S sub n is equal to this expression. Now, I went ahead and just did this part myself. So it gave me 1 over 2 times 4 plus 1 over 4 times 6 plus 1 over 6 times 8 plus 1 over 8 times 10. So I just looked at that and I said, well, I know that the first term, that's the product in the denominator, is always going to be twice whatever n is. This is n equals 1, n equals 2, n equals 3, n equals 4. So that first factor in the denominator, it's just 2n. The second factor in the denominator is always going to be 2n plus 2 because I can see it's going up by 2 each time. That's where I'm getting the 2n from. But that first term in this factor is a 4. So you'd say, well, if this is n equals 1, 4 can be represented by 2n plus 2. And that's going to represent the second factor for every value of n all the way after. Here's n equals 4. You'd say, well, that's 2 times 4 plus 2. You get the 10 there. So now I can say, okay, this is my general term. How about I go ahead and find the second partial sum? Well, that's the sum of the first two terms in the series. You got your 1 over 8 plus 1 over 24. I got 1/6 when I did that. Your fourth partial sum, well, it's your second partial sum plus the third and fourth term. Well, the third term here, I had 1 over 48 plus the fourth term, that's the 1 over 80. When I added those, I got to a fraction of 1/5. Now my sixth partial sum term, you take the sum of the first four, which we already found out, plus the fifth term. And here's where I had to use this and say, well, if I'm at the fifth term, the first product in the denominator is going to be 10. The second one's 12. So I get 1 over 10 times 12. The sixth term would be 1 over 12 times 14. So I have 1/5 plus 1 over 120 plus 1 over 168. I get my 3 over 14 there for the final answer. Now, fortunately, the next couple of problems get much more gorgeous than those. So that was the number 4 and now number 5. You'll see number 5 asks us to find the sum of a series. Now, finding this sum of a series, you can't do like we've done in our other problems. This type of series is what's called a telescoping series. So the way that we're going to handle a telescoping series, it's similar to how we went back and did partial fractions for our integration back in section 7.5. So notice here, I have the summation of 1 over 4n squared plus 9. I recognize that that denominator is a difference of two perfect squares. Could factor to be 2n plus 3 times 2n minus 3. So I factor it to that. Now, in order to represent what this is equal to and make sense out of it a little bit more, I'm going to separate this fraction into two partial fractions. And I can say, for every linear denominator, there needs to be a constant numerator. So a over 2n plus 3 plus b over 2n minus 3. Now, I multiply by that least common denominator, 2n plus 3, 2n minus 3 on both sides, and I'll get 1 is equal to a times 2n minus 3 plus b times 2n plus 3. Okay, now I can go in and say, I should be able to solve for a if I let the denominator 2n plus 3 equal 0. Well, that would give me 2n is equal to negative 3, n is equal to negative 3 over 2. So please notice, I let n equal negative 3 over 2. When I do that, my left-hand side is still 1 because there are no n's left in it. On the right-hand side, if you plug the negative 3 over 2 into this expression, b would be multiplied by 0. Plug a negative 3 over 2 in right here, you'll get 2 times negative 3 over 2 is negative 3. Negative 3 minus 3 gives me a times negative 6. So now I know negative 6a is equal to 1, thus a is equal to negative 1/6. You do the same thing to solve for b by letting n equal positive 3 over 2. When you do, a gets multiplied by 0, b gets multiplied by a positive 6. So then I can say, well, clearly then b is equal to positive 1 over 6. So I have a is negative 1 over 6, b is positive 1 over 6. So now I go back to my original problem and I can say, all right, then this series of n equals 1 to infinity of 1 over 4n squared minus n is equal to, now what I've done, since both of these had a 1/6 in it, I went ahead and factored that 1/6 out. And then, instead of putting the negative term first, I wanted to go with the positive term first. So I said, well, if I factor a 1/6 out, I'll just have a 1 in the numerator, and it's going to be 1 over 2n minus 3. Now, a was the negative term, so I'll have minus 1 over 2n plus 3. I think it helps to put the positive before the negative in here. Now, I can say, all right, I've factored that 1/6 out. I'll have the limit as n approaches infinity, because again, remember, this summation is from n is equal to 1 all the way to infinity. So I need to think about what each of these terms are going to be. So the first thing I do is I say, well, let's plug in what happens when n is 1. And then you can say, well, if n is 1, you're going to have 1 over 2 minus 3. That's 1 over negative 1. That's that term. Minus 1 over 2 times 1 plus 3. That's going to be 1/5. So I have negative 1 minus 1/5. The second term, if you plug in a 2 there, this denominator would be a positive 1. So you have 1 over 1 minus 1 over 2 times 2 plus 3. That's going to be minus 1/7. The third term, this is when n is 3. You'd say, well, if I plug an n equals 3 in, this first fraction is going to be 1 over 6 minus 3. That's 1/3. The second fraction is going to be 1 over 6 plus 3. It's going to be 1/9. So I get 1/3 minus 1/9. Now here's where you start to realize, okay, almost every single term in here is going to cancel out. Right here, please notice the first term, or the first part of the fourth term. You'd say, well, I need to plug in an n equals 4. This would be 1 over 2 times 4 minus 3. That'd be 1 over 8 minus 3 is 1/5. Well, this 1/5 and every first part of every successive term hereafter is just going to cancel with the second term of one previous to it. So I can say this is going to be a plus 1/5. What would be the first part of my fifth term? It'd be a positive 1/7, which is going to cancel with this 1/7. Every single one of these second terms are going to cancel through here with the first term. Now, the ones that didn't cancel, though, please go back and make sure you see, well, all of these are canceling, and every first term after the first 3 terms are going to cancel. Well, you're not canceling the first part of any of the first 3 terms. Then you won't cancel the last part of any one of the last 3 terms. So that's why I put what the last 3 terms would be, with the last term being the nth term. This is the n minus first term, and this is the n minus second term. So I can say, well, those terms won't cancel out either. Everything else will cancel out except for these parts of the first three and these parts of the last three. So then I can go in and say, well, then this summation is going to equal 1/6, the limit as n approaches infinity. The first three terms that don't cancel, and then the last three terms that don't cancel. Am I at all concerned about them? No. Why no? Please notice, n is going to infinity. So these last three terms all go to 0. 1 divided by 2 times infinity plus 3, 0. 1 divided by 2 times infinity plus 1, 0. These become negligible as you take your limit as n approaches infinity. So I can say, well, okay, I'm going to have a -1 plus 1. Those two just cancel each other out. This is all going to simplify to just be 1/6 times 1/3. You get your final answer of 1/18 there. Love that problem. That's gorgeous. Now, if one telescoping problem wasn't enough, we've got another. Number 6 is cool because instead of telling you the summation and what the telescoping function was in terms of n inside, they don't do that. So they give me this, 1/9 times 26 plus 1/26 times 43 plus 1/43 times 60 plus 1/60 times 77. So what am I supposed to do here in order to come up with this? Here's what I did, guys. I looked at the first factor in the denominator and said, what's the difference from here to here to here to here? And you say, well, it's increasing by 17 each time. 9 plus 17 is 26. 26 plus 17 is 43. 43 plus 17 is 60. So this has to have a 17n for that factor. But you say, well, if you let the first factor be 17n, your first term would be 17, and it's just a 9. Well, okay, 9 is 8 less than 17. That's why I called my first factor 17n minus 8. Now, please notice, when n is 2, that'd be 17 times 2 is 34, minus 8 is 26. When n is 3, 17 times 3 is 51, minus 8 is 43. Gorgeous! When n is 4, 17 times 4 is 68, minus 8 is 60. So I can say, okay, I got my 17n minus 8. What about the second factor? Once again, I just recognized it's also going up by a factor of 17. So I knew it was a 17n as well. But instead of saying 17n minus 8, I can say, well, that first term, 26, that's going to be 17 plus 9. So I'm going to have to say that second factor is 17n plus 9, and that would account for every second term in here for n equals 1, n equals 2, n equals 3, n equals 4. For that fourth one, you would say, well, 17 times 4, that's going to give you 68. 68 plus 9 gives you the 77 there for that term. So I can say, yes, this is the a sub n notation for what these formulas are. Now, I had to get to that. If you couldn't get to that, you're not able to solve the telescoping series. So I'll say, okay, I recognize this as a telescoping series, and I break it down into its simpler partial fractions. When I do that, the work is below. I just multiplied by the least common denominator on each side and got 1 is equal to a times 17n plus 9 plus b times 17n minus 8. Then I can say, well, I should be able to solve for a if I let 17n minus 8 equal 0. That gave me 17n is equal to 8, n is equal to 8/17. If I allow n to equal 8/17, your b is going to be multiplied by 0. Your a is going to be multiplied by 17 times 8/17, which will give you 8. 8 plus 9 gives you the 17. So I can quickly see, hey, 17a is 1, a is 1/17. Similarly, if you set the denominator below b to equal 0, you should be able to solve for it. That's going to be equal 0, and 17n is equal to -9, which tells you n needs to equal -9 over 17. That's what I plugged in right here. Kind of ugly writing there. I plugged in the -9 over 17 into this function. When I do, your a is multiplied by 0. Your b, you'd have 17 times -9 over 17. That's going to be -9. -9 minus 8 gives you back the negative 17. Then you say, okay, so negative 17 times b is 1. Thus, b is negative 1 over 17. So now I take this summation and I can say, all right, if I allow this summation, and I'm going to call it S sub n here, but it's equal to all of these terms of n, and I would rather go ahead and instead of saying it's 1/17 over this term and then minus 1/17 over this term, I'm going to factor that 1/17 outside of the summation. And then my first term is going to be 1 over 17n minus 8. And then I will have a minus 1 over 17n plus 9. Okay, so now this sum is going to equal 1/17. Please remember, this is an infinite summation. Anytime you don't put indices, it's because the indices are implied to be from n equals 1 to infinity. Anytime it's from 1 to infinity, there is no need to put them there. So I can say, all right, n is approaching infinity. But what's the first term going to be? You say, well, when you plug in your first term, you'll have 1 over 17 minus 8, which is 1 over 9, minus 1 over 17 plus 9, which is 1 over 26. So my first term is going to be 1/9 minus 1/26. It's extremely important not to try to simplify that. You'll lose the pattern. You need to keep it first part of the first term, second part of the first term. Now I go to my second term. This is when n is 2. Your first term is going to be 1 over 34 minus 8, gives you plus 1 over 26. Your second term, minus 1 over be 34 plus 9, which is 1 over 43. And then instantly I see, guys, the first term of every successive term in here, or the first part of every successive term in here is going to cancel with the last part. So this 1 over 26 is going to cancel with this minus 1 over 26. What do you absolutely already know the very first part of the third term is going to be? It's going to be a plus 1 over 43. It'll cancel that one out. But nothing's ever going to cancel out the 1 over 9. On the same manner, nothing would ever cancel out the very last term of this series. So you can't cancel out the first term nor the last term. Every other term will cancel. So I just had, well, this is equal to 1/17. The limit as n approaches infinity of 1/9 minus 1 over 17n plus 9. That 1 over 17n plus 9 becomes irrelevant because you take the limit as n approaches infinity, and that term goes to 0. So our final answer is just 1/17 times 1/9, and we get our 1 over 153. That is just a gorgeous problem there, guys. Wonderful stuff. Now, that's probably the two most fun problems in the section. Every problem hereafter, pretty quick, actually. Let me look at number 7 with you. Number 7 tells you it's a geometric series. From our notes, you're supposed to remember the summation formula of any geometric series is C over 1 minus R, and that's where C is simply the first term of your series, and R is the common ratio, what you're going to have to multiply that first term and every successive term to get to the next term. Okay, so in this first problem here, I had to recognize C. Well, C is just the first term, so plug in n equals 2 into this expression, and you'll get 7 times negative 3 over 8, and both of those are going to be to the second power. So I just said in my head, well, that's going to be 7 times 9 is 63 over 8 squared, 64. My first term is 63/64. Now, I can see the common ratio each time. I have a negative 3 over 8 that's going to consistently be another power of n throughout each successive term. So the common ratio in this problem is negative 3 over 8. Please notice you could have written this as 7 times the group, negative 3 over 8 to the n. That's our common ratio. So now I go back to my problem and I can say, well, 63 over 64 is my first term over 1 minus the common ratio of negative 3 over 8. So what I did is I just said, well, I want to get rid of the fractions in there. I'm going to multiply by 64 in the numerator and denominator. When I do that in the numerator, I get my 63. In the denominator, you would have 64, and then it would be plus 3 times 8 is 24. 64 plus 24, you get your 63 over 88. That answer is great. Now, in this next one, I'll actually admit to making an error here, but I tried to cover it on the sheet and act like it wasn't an error. So the first thing I did is I looked at this series here and I just said, okay, it's a geometric series. You have something raised to the n power. So I just went ahead and said, well, the summation formula is c over 1 minus r. And if you think about what c would be in this case, it's just the first term. Well, the first term would be when n is 0. And if n is 0, this group is to the 0 power is 1. So I said 1 over 1 minus the common ratio, which would be 10 pi over e. And then I tried to simplify by multiplying by e over e, and I got to this expression. Why is this expression wrong? And how do we already know it's wrong? A couple of reasons. Because if you think about 10 pi over e, 10 pi positive number, e positive number, and you're always raising it to positive exponents. Okay, it's impossible to ever get a negative term in that summation. But look at this. E divided by e minus 10 pi, that denominator is negative, which would make this fraction negative. You can't take a sum of positive numbers and get a negative. Okay, so that's just telling you that's impossible. There's something wrong. What have I done wrong? I haven't really done anything wrong. The algebra here is correct. I'll say, or I'll pretend I did that intentionally just to show you if you try to do it, the algebra stuff, it'll work out, but your answer is wrong. The reason it's wrong is it should have never been done in the first place. Why should have it never been done in the first place? Because the summation formula for the geometric series only works if the series converges. How do you know if the series converges? The common ratio has to be less than 1. Now that needs to make sense to you guys, because think about if the common ratio is not less than 1. If the common ratio is not less than 1, then you're adding values that are getting increasingly larger and larger and larger and larger. How can you add infinitely many values that continually get larger? Quick answer is you can't. It's going to diverge to infinity. So in order for a geometric series to converge and come to some nice answer, that common ratio has to be less than 1. Meaning every term of your series is going to get gradually smaller and smaller and smaller. Okay, so I look at this and I say, well, okay, 10 pi over e, that is way larger than 1. So the terms of this series are getting larger and the summation formula is invalid. So what do you say? Well, you say that the series diverges to infinity. Now what they want to achieve is just that the limit does not exist. Really, I would prefer infinity as an answer, but they want does not exist. For the next one here, and again, it's a geometric series. Anytime we have any term raised to a power, now this one's a little bit of disguise, and you have to understand your properties of exponential functions here. I know that e to the negative 5 minus 2n, that's the same thing as e to the negative 5 times e to the negative 2n. So what I did is I said, well, I'm going to take that e to the negative 5 and then e to the negative 2n, that's the same thing as 1 over e squared raised to the n. Why would I do this? Now, hopefully you see, okay, yeah, this is the same thing as e to the negative 2. E to the negative 2 raised to the n, that's the same thing as e to the negative 2n. But why would I write it this way? Because this way, it helps me easily see what my R value is here. So every successive term of this series, every time n goes to another term, whether n is 1, 2, 3, 4, 5, 6, what's happening is you're continually multiplying by a factor of 1 over e squared each and every time. I had to write it this way in order to see that. So now, when I go in and I say, well, all right, yes, you did need to know what your common ratio is, the 1 over e squared, but you also need to know what your first term is. I know that this one will have a solution since 1 over e squared is less than 1. This geometric series will converge. My first value that I call c, you're just plugging the 3 into this expression. You'd have negative 5 minus 2 times 3. That's going to be negative 5 minus 6. You got e to the negative 11th power for your first term. So now my formula, this series will converge to the fraction of the first term divided by 1 minus the common ratio. That first term, e to the negative 11th, divided by 1 minus the common ratio. Now, instead of writing it as a fraction, which I could have, 1 over e squared, I went ahead and wrote it as e to the negative 2 here. And then I could see I could clear all negative exponents in this expression if I just multiplied by e to the 11th. That's what I did. E to the negative 11 times e to the 11 gives me a 1 in the numerator. And in the denominator, it would distribute to give me e to the 11th minus e to the 9th. I like that answer. It probably would have accepted a lesser form of the answer, probably that form right there, but this answer is beautiful here. All right, up next, number 10. The only tricky part of number 10 is they didn't necessarily give you the expression. They didn't really have to. What you would do here, if you're trying to find the summation of 3 to the second over 4 cubed plus 3 to the third over 4 to the fourth plus 3 to the fourth over 4 to the fifth. We know that this is a geometric series. And first of all, how do you know it's a geometric series? Because I know each numerator is being multiplied by 3, each denominator is being multiplied by 4. So I can say, oh, okay, it's a geometric series since every single term is going to be multiplied by an increasing power of 3/4. Yes. Now, the sum of this geometric series, and I know that there will be a sum since 3/4 is less than 1, I can just say it's the first term over 1 minus the common ratio of 3/4. In simplifying this expression, I multiplied by 4 cubed in the numerator and denominator. When I did that in the numerator, of course, I got a 3 squared, the 4 cubed cancels. In the denominator, you'll get 4 cubed minus 3 times 4 squared. That 4 to the first canceled with one of these. And then that simplified easily to 9 over 64 minus 3 times 16 is 48. 64 minus 48 is 16. You get your final fractional answer of 9/16 there. Similarly, number 11 is pretty much the same thing. It gives you these terms here, and you have to see what the sum of the series is. And when I was doing that, I actually looked at between the first term and second term. It really would have been easier if you went from the third term to the fourth term. That's the most obvious one. But I went from the first to second, and I said, well, what's going on from here to here? I would have to multiply this numerator by 1/10, and I would have to multiply the denominator by 1/9. So I was thinking of it as this. I said, well, I have to multiply the numerator by 1/10 and the denominator by 1/9. But then I said, but if you divide by a fraction, you multiply by the reciprocal of that fraction. So this is 1 over 10 times 9 over 1, and I got the common ratio of 9 over 10. Now, I did that from looking at what happened from the first term to the second term. It'd have been so much easier if you just said, John, why don't you just look from the third term to the fourth term, and clearly it's getting multiplied by a factor of 9 over 10. And I should have, but it's going to work for any one of those. So I can say, okay, my common factor that's continually getting multiplied is 9 over 10. Since that's less than 1, this geometric series will have a sum. The sum of that series is going to be the first term, C, 100 over 81, divided by 1 minus the common ratio of 9/10. So I just went ahead and multiplied by the least common denominator of 81 times 10. I multiplied by 810 in the numerator and denominator. When I did, my numerator gave me 1,000. My denominator is 810. And then I would have had 81 times 9, which is 729. 810 minus 729 gave me an 81 for that denominator. Worked out really nicely. Now, the last couple of questions here. Number 12. Now, this one you may have already known just from your arithmetic knowledge, but let me go ahead and show the calculus logic in it. It wanted us to write the repeating decimal 0.43, 43, 43, on and on and on, as a fraction. Now, this is using the calculus summation of a geometric series. So what I had to recognize is that, well, the 4-3 is the repeating part. This first 43, this is known as 43 over 100ths. And then you say, okay, that's tens, hundreds, thousands, 10,000s. That next 43 is 43 over 10,000. So you say, okay, here's your first term of the series. Here's your second term of the series. What do we know is happening? Well, you know it's the numerator is getting multiplied by 1 because it's not changing. Your denominator is getting multiplied by 100 every time you go 2 more decimal places. So you can say, oh, well, this is a geometric series with a common ratio of 1/100th and a first term of 43 over 100. So that's what I did. I said, this is the sum of a geometric series. 43 over 100 divided by 1 minus the common ratio. Let's multiply by 100 here. Your numerator is 43. Your denominator is 100 minus 1, which of course is 99. And you can say, well, this is just 43 over 99 to get the 0.43 repeating. Now, this last problem, I could see giving some students some stress, but it's really, really easy. Let me try to make sure you see that. So you already see I've got the answer in. Let's talk about where that answer came from. It says, in economics, the multiplier effect refers to the fact that when an injection of money to consumers, the consumers spend a certain percentage of it. The amount recirculates through the economy and adds additional income, which comes back to customers, and of which they spend the same percentage. This process repeats indefinitely, or as we're supposed to assume, infinitely many times, circulating additional money throughout the economy. Suppose that in order to stimulate the economy, the government institutes a tax cut of $16 billion. If taxpayers are known to save 7% of any additional money that they receive and spend 93% of it, how much total money will be circulated in the economy by that single $16 billion tax cut? And now, a lot of people are just overwhelmed when they see this correct answer. Notice my correct answer, it's $229 billion. That's how much money goes into the economy by one $16 billion tax cut. That doesn't seem to make sense. Here's how it makes sense. Let me try to explain this to you. So, of that initial 16 billion, if you're trying to think about the instant impact into the economy, if we are to assume what the problem stipulates, that 93% is spent, then you'd say, well, then you're going to have 93% of that $16 billion tax cut spent, and that's going to be $14.88 billion spent initially. Okay, but here's the thing. That amount spent that you give somebody else, that's money that they wouldn't have had without that, and then they'll go out and spend it. So this is going to continue on and on and on and on. So if we're thinking about how much money one $16 billion tax cut puts into the economy, then you'd have a total amount of additional money flowed in. You'd say, well, I'm going to let n equal 0. Why would n equal 0 here? Because that original 16 billion is going into the economy, plus every 93% of it successfully after that. So I need my initial amount C to be 16. I can only enable that if I allow n to start at 0. And then when n is 1, it'll be 16 times 0.93. That's where the 14.88 comes from. Now, this is going to continue on and on and on again. So you say, well, this is just a geometric series with an R value of 0.93 because it's going to continue every time it's spent. So you have the 16 over 1 minus 0.93. So that simplifies down to 16 divided by 0.07. Now, when I did that, the more exact or precise answer would be 228.571, and this is in billions of dollars. But Achieve is wanting it rounded to the nearest billion, which of course is going to go to 229 billion for the scenario that I was given. But still, to me, that seems just overwhelmingly large amount for one $16 billion tax cut, but it kind of does go to show the power of one tax cut because of its continual effect on and on and on. All right, guys, that finishes it for this section. Hopefully this has helped you out with any questions that you should have. In our next section, we'll be looking at different techniques to find out how a series either converges or diverges. Right now, about the only one that we have is, well, actually two. We have the telescoping series and the geometric series. We'll be seeing a bunch more fun stuff